these are the notes on modeling chemical reactions. For today, you are going to go through and complete this evaluating chemical reactions activity. I'm going to kind of go through the intro on it, and then you're going to pop back to these notes for the kind of remainder of the notes on here. So in this activity, this unit is on chemical reactions. You are going to practice counting atoms in an equation and using dots to represent atoms with that. And so here's this intro for you. This talks about using bingo chips because we aren't in person. We don't have those bingo chips. You're going to be able to use colored dots. And I would almost recommend kind of setting up your highlighters so that you can kind of use those colored dots to represent different atoms as your bingo chips. So this first part, as you're going through, through this first part, identifying the elements, make sure you're reading directions as you go through. I know I'm jumping a little bit. It says refer to data table 1 and identifying atoms in the formula. And so this first one, name and use, so we have silicon dioxide, which is used in sand. The formula is provided for us. And if I'm looking at what are the atoms in the formula, including the number, I am going to go ahead and look at this, and I can see that I have silicone, Si, separated capital letter lowercase, so that I belongs with the S, so silicone, and because there's no subscript after it, I know I have one silicone atom. My oxygen, then oxygen, that O2 there, oxygen is the element, our atomic symbol, our element name is oxygen, and I have 2 atoms because of that subscript of 2 on the oxygen. And just as a reminder, if anything doesn't have a subscript, that means it's a kind of a 1, but we don't write out the 1s because scientists are lazy with that. And so there's the directions down below. We listed each element, writing both the symbol and the name. Use your periodic table, and then write the number of atoms of each as well. So go ahead and complete that, and then go on to the next bit. All right, so for this next part, we are going to model chemical reactions. So when we have chemicals interacting with each other or reacting. And so there's that data table 2, which I have on the next page. And it says select different colored chips. We're going to just do different dots or circles to represent each different atom. And then for the first reaction, build one representative particle of each reactant on the left side of your work surface and one molecule of each product on the right side. So we're just starting with one of each. Some examples of representative particles are here. We're going to kind of draw those connected to one another. And so when we look at this example down below, here's my hydrogen, my representative particles here. I have 2 hydrogens, that's that H2. I have oxygen, that's O2. And then I have H2O. So I'm going to have 1 oxygen and 2 hydrogens in that representative particle. And as we go through and look at this, we have 1 of each. That's what we're starting with. And now it says draw or imagine an arrow between the reactants. Here's my arrow. And now when we look at this, if I just have hydrogen plus oxygen gives me H2O, when I'm looking at my number of like atoms, I only have 2 hydrogens on the left here, but that's great. I have 2 hydrogens on the right. And so those are balanced. I have the same hydrogens that I started with. But when I look, my oxygens, I have 2 oxygens on the left side of my arrow, but I only have 1 oxygen on the right. So then this step 7 is saying if the number of each like atom is equal, the equation is balanced. If the number is not equal, add additional molecules to the appropriate sides until the total number of atoms on the reactant side is equal to the total on the product side. And reactants are on our left because those are the things that are reacting. Products are on the right, the things being produced. And so when we look at this, if I look at kind of this original, if I imagine this isn't here and this isn't here, 2 hydrogens and 2 hydrogens, great. but 2 oxygens and 1 oxygen, that's not great. And so I need to then draw another H2O pair so that now I have 2 oxygens and 2 oxygens, but now that means instead of having 2 hydrogens on the right, I have 4. So then I'm going to need to add another H2 pair. And then once we have part C, write the number of each atom as a coefficient in the space in front of the chemical. If there's only one of that chemical, you do not need to write the coefficient of 1, just leave the space blank. So we have 2 H2s, and hydrogen is diatomic, and so that's why this is an H2. So we have 2 H2s, we have 1 O2, oxygen is also diatomic, and then I have 2 H2Os. So adding those coefficients to say how many of each did I need in order for the number of hydrogens on the left to equal the number of hydrogens on the right. Same thing with my oxygens. All right, so let's go through the first one in this data table, doing that molecular representation, and then you'll be able to work on the rest on your own. So with this one, PbCl2, the states of matter, we've talked about those. Those aren't going to impact how we draw because we're going to just draw each of those different atoms. And so let's see, I'm going to make my leads orange. I'm going to make my chlorines red. I'm going to make my sodiums green. And then I'm going to, we can keep a polyatomic together. I'm going to keep those, or I'm going to make those yellow. All right, so I've got 1 lead. So I've got Pb, and then I've got Cl, Cl, as I draw that representative particle. So there's my lead, and then I have 2 chlorines. And I'm going to just put these close together to kind of represent that molecule. All right, and then I've got 2 sodiums, and then I have an SO4. So I've got 2 greens and 1 yellow. And we could separate our SO4. One thing we're going to find as we're balancing is if I have that same grouping on both sides of those polyatomic ions, that I can keep those together because that ratio stays the same. And then I'm going to have 1 lead and 1 SO4. So that's going to be a yellow and an orange. And then I've got 1 sodium and 1 chlorine. Sodium's green and chlorine is red. And again, I just picked those as random. Okay, so now let's count and let's look. So if the number of each like atom is equal, the equation is balanced. If the number is not equal, we need to add additional molecules to the appropriate sides until the total number of atoms in the reaction side is equal to the total in the product side. I'm going to just start with kind of my first one. So lead, I have 1 lead and I have 1 lead. So those are good. So I'm going to move on. I have 2 chlorines on the left, but only 1 chlorine on the right. So in order to, we can't get rid of any chlorines. I can't get rid of one of these. So in order to get 2 chlorines over here to match, I'm going to need another representative particle. So I'm going to duplicate that. So now I have 2 of those. So I'm going to cross it out. So now I have 2 chlorines. So my lead's matched, my chlorines matched. So let's keep going. Sodiums. And I'm going to count with what now I have, now that I added another NaCl. I have 2 sodiums on the left. I now have 2 sodiums on the right. Great. And lastly, I'm going to use black instead of yellow. I have 1 SO4 on the left and I have 1 SO4 on the right. So all of those match. I only had to adjust how many representative particles of sodium chloride I had. And so in order to show that I have 1 PbCl2, 1 Na2SO4, 1 PbSO4, And this one I have 2 NaCl's. I'm going to put a 2 coefficient in front to represent that I have 2 of these. All right, take some time, finish the rest of that data table, reach out with any questions that you have, and then come back to this video and we're going to kind of do a little bit of a wrap up. All right, so as we're starting to talk about chemical reactions, we have a couple different ways we can model chemical reactions. And so the ways we can do that, we have word equations, we have skeleton equations, we have balanced equations, and we have the material state. And so one thing you worked on up here is you took a skeleton equation and you balanced those. And so before we had any numbers, any coefficients, what you started with in each of these was a skeleton equation. Once I put this 2, though, that's a balanced chemical equation because I'm showing how I'm going to balance those. And I actually think we should add molecular representation on here as well for another way we could show this representation. We don't often draw out the molecular representation because it takes a lot of time. So once we are comfortable with this, then we really use that balanced equation kind of as our kind of shortcut in science. So with word equations, one way to model a chemical equation is with words. This is like thinking about a reaction as a recipe. And so if we look at, or if we think about, well, what part of a baking process would be the reactants? Well, if you're making bread, you've got flour, eggs, milk, salt, baking powder, and oil. Those things are our reactants on the left. And if we're to write out what are their names, then that's modeling this with words. And then they react to produce bread. That's going to be our product. What do we get out after baking? And so those initial ingredients are our reactants. And then the products is what do we get after that baking? And so this representation in words is one way that we can talk about equations. In our chemistry setting, if we kind of go back to this example from here, this one, we have lead 2 chloride plus sodium sulfate produces lead 2 sulfate and sodium chloride. And so instead of writing out NaCl, I'm saying sodium chloride. That is a way to show a chemical reaction with words. All right. Other ways to represent, so our word equation, if we say hydrogen plus oxygen produces water, our skeleton equation would then be to say H2 plus O2 produces H2O. That one, just like that kind of initial example that the worksheet walked us through, this isn't balanced, but these are the chemicals that we have. We would then need to, if we want to get that balanced equation, that's when we add in those coefficients to say, okay, I need 2 H2Os to get 2 oxygens, and I need 2 H2s to get 4 hydrogens on both sides. So then that's also our balanced. And then material state, we are going to often see not just the chemical, but we're going to see the state of matter to say, okay, I have hydrogen gas plus oxygen gas, and it's producing liquid water, H2O. So material state showing the states of matter within the reaction. Those states don't impact balancing. It just tells us information about what those chemicals look like and what state they're in. So balancing equations, our skeleton equation again just has what are the parts and what does it form. The balanced equation, now our parts have to match up with the number we need in order to form that bicycle. And so as we're looking at this, if the parts of a bike are frames, a frame, wheel, handlebar, and a pedal, and we combine that to get a bike. But when we actually look at this bike, we have one frame, but we have 2 wheels. So we need twice as many of those. Handlebar, we have 1 handlebar, and our pedal, we need 2 pedals, 1 on each side. And so then that makes that bike compound FW2HP2. And so by putting in those coefficients of I need 2 wheels, I need 2 pedals, That's what gives us the balanced equation from our skeleton equation. So comparing these, the same components are in both, but the actual number of reactants needed to make those product is not included in a skeleton equation. All right, energy of chemical reactions. So how do chemical reactions occur and why? Chemical potential energy is stored in the bonds between atoms. So when bonds form, energy in the form of heat is released. So breaking bonds, energy is needed, and then that energy is released when bonds are formed. And so the law of the conservation of energy says that energy can't be made or destroyed. And so reactions that release more energy than they need are called exothermic. Reactions that release less energy than they need are called endothermic. And we're going to actually talk more about this in our thermodynamics unit. And so what's causing those reactions? For a reaction to occur, particles have to collide with enough energy to break bonds. The reaction rate describes how fast a reaction's occurring. So often if we increase temperature, then we're going to have more collisions. Our reaction is going to occur faster. And we are, again, going to spend more time talking about that on our chemical reaction unit. All right, so these were the notes on modeling chemical reactions. Make sure you finished up this evaluating chemical reactions activity, and please reach out if you have any questions.